Good morning, students. Today we are going to discuss a very important topic, torque and angular momentum. Now let us start with the torque or moment of force. Now what is torque? Torque is nothing but a rotational force, or you can say force which define an object by its rotational motion can be defined as a torque. So the impact of torque is nothing but to create some rotational impact on the object where you are applying. If you apply force and if the object experience some rotational motion, then you can say it is nothing but a torque. Now torque or moment of force, that one we are trying to define. In the figure you see you do have a coordinate system x, y and z. Now you do have a particle at A whose position vector is r vector. Now here we are applying a force F vector to the particle which is at A by an angle theta with the position vector. Now here in the diagram we have dropped a perpendicular from the origin of the coordinate system on the line of action of the force, and that one we have defined by OM, which is nothing but is your small d. So let me go through the statement. The turning effect of force is called as moment of force or torque. So if some force creates some rotational impact on an object, then you can say that that force is nothing but a torque. Now in the figure in triangle OMA, if you define sin theta is your perpendicular by hypotenuse. Perpendicular is your OM and hypotenuse is your OA. So sin theta equal to OM is your D and OA is your R. So D equal to R sin theta. And D is nothing but the lever arm or moment arm of force. So you can say OM is nothing but is your lever arm or moment arm of force. Now as per the definition, torque is defined as the product of the magnitude of the force acting on the particle and the lever arm, and the lever arm is nothing but is your small d. So torque equal to as per the definition F and D is nothing but is your R sin theta. So in vector form you can say tau vector equal to R vector cross F vector. So this is your rotational impact of force, and that rotational impact of force is nothing but the moment of force, and that one we can define as your torque. Now direction of torque is defined by right hand screw rule. Now you see in tau equal to Fr sin theta, so you can express this one in terms of vector product, because of vector product already you know. If A cross B is a vector product, then magnitude is nothing but is your AB sin theta. So Fr sin theta, so in vector form you can write, in vector product form you can write tau vector equal to R vector cross F vector. So you can define the direction of torque by using right hand screw rule. So right hand screw rule, I think all of you know, that one is used to define the direction of vector product. Now let me go for the rectangular components of torque. So in torque we do have R vector and F vector. So in 3 dimension, R vector can be specified as your x I cap plus y j cap plus z k cap, and F vector can be represented by fx I cap, fy j cap plus fz k cap. So tau vector equal to R vector cross F vector, and I cap, j cap, k cap, that one is the definition of vector product, I cap, j cap and k cap, and x, y, z, and fx, fy, fz. So if you take the definition of tau vector equal to R vector cross F vector, then I cap y fz minus z fy minus j cap x, if you have to consider j, you have to eliminate j cap, you have to eliminate the row and column part. So you do have x fz minus z fx, and k cap equal to k cap within bracket x fy minus y fx. So in terms of components, tau vector can be expressed as tau x I cap, tau y j cap, tau z k cap. So if you compare tau x equal to y fz minus z fy, tau y equal to, you can change the negative sign. So for that you have to write z fx minus x fz, and tau z equal to x fy minus y fx. So these are the rectangular components of torque. and it comes from the cross product definition. Now next one, you will try to define angular momentum. So it is same as that of the torque. Now in place of force, what we have given here, momentum, that is your linear momentum, p vector, small p vector, which is nothing but within bracket we have written mass into velocity. Suppose you do have a particle whose position vector is r vector, and the particle moves with velocity v vector at an angle theta with the position vector. So if the particle moves with the velocity v vector at an angle theta, then definitely it carries linear momentum, because linear momentum is nothing but is your mass into velocity. So angular momentum is the moment of linear momentum, you can say, and torque is nothing but the moment of force, and angular momentum is the moment of linear momentum. So if you consider the triangle OMA, so it's your OM equal to r sin theta. So that part we are not writing it in details because it is already specified how it comes. So we have written directly here. If you take the sin theta, then it comes out OM equal to r sin theta. So as per the definition, angular momentum is the product of the magnitude of linear momentum and the perpendicular distance from the axis of rotation. So axis of rotation is nothing but the axis which passes through the origin. Okay, so you can say that OM is the perpendicular distance from the origin to the line of action of linear momentum. So as per the definition, linear momentum and the perpendicular distance from the axis of rotation is nothing but is your angular momentum. So L equal to r sin theta p. So in vector form, you can write L vector equal to r vector cross p vector. So similarly, you can find the rectangular components of angular momentum. So I am not trying here, you try it in home and try to find out the rectangular components of angular momentum. So please go through this topic and try to find out your queries, because this topic is very important for the numericals. So this is all about. Please do check and try to find out your queries. Thank you.